Okay, it was brought to my attention that we actually don't have class on Thursday. So yesterday when I said that you would have your Chapter 3 quiz on Thursday and I wasn't sure what we would do yet on Friday, that is incorrect. There's no school on Thursday. So Friday you will have your Chapter 3 quiz and everything else will remain the same. Okay? All right, so don't forget my office hours are from 1 to 4 every day, and yeah, so that is it. That's the new change. You now have your Chapter 3 quiz on Friday rather than Thursday, because Thursday we have no school, so you can spend that day studying. Okie dokie. We are going to start our first review session for Chapter 3. So I'm going to just go over the things that people asked the people that did the homework. Thank you for doing that. I'm going to go over the things that you wanted to go over. So remember, from 3.1 was all about forces. Remember that a force is a push or a pull. Any push, any pull. We measure force in the unit of newtons. And I gave you some examples. Remember that it's not like forces aren't necessarily easy to see. For example, the ground and our feet. We know now, because of Newton's third law, that our feet are pushing on the ground, and if our feet are pushing on the ground, that means our feet are exerting a force on the ground, and for every action force, there's a reaction force. So that means that the ground is pushing back up on our feet. We have the atmosphere exerting a force on us. We have all sorts of forces that are being exerted on us, and we are exerting on objects and each other and different things at all times. So, a net force. We need to talk about a net force. Some of you said you were confused about that. So, what is it? It's the sum of all the forces acting on an object. When two or more forces act on an object at the same time, the forces combine to form what's called a net force. We have two types of net force we discussed. Remember, we talked about unbalanced forces. Unbalanced forces are those that cause an object to move. And all forces that are being exerted give a net force that is greater than 0. So anytime we have a net force greater than 0, we have an unbalanced force acting upon, an unbalanced net force acting upon the object. Balanced forces cause an object to remain stationary. So when all of the forces acting on an object give a net force equal to 0, then we have a balanced force and we have no motion, right? So let's look at some examples. So we can draw these are all examples of unbalanced forces. Remember, they cause the object to move. So we have our individual forces. We have our object, which is the square. We always draw our object as the square, remember? We have two individual forces acting here on this object. We have two 10-Newton forces in the rightward direction acting on this object. That gives us a total net force when we add them together. Since they're in the same direction, we can add them together, of 20 newtons to the right. We have an unbalanced force here, where someone is pulling to the left with 5 newtons and another object or person is pulling to the right with 15 newtons. When we add those together, remember our rules, I have them written right here. Our rules for drawing forces, this is the second rule. We subtract forces that are in the opposite direction. We subtract 5, negative 5 plus 15, or 5 minus 15, gives us an overall net force of 10 newtons in the rightward direction. All right, finally, our third unbalanced force down here, we have 12 newtons of force in the leftward direction and 8 newtons of force in the rightward direction. So we are going to subtract 8 from 12, and we get a net force, a net unbalanced net force of 4 newtons to the left. All right? So all of these, because there's a force being exerted on the object, they're all moving. This one's moving, this one's moving, this one's moving. This is different from our our balanced forces, which cause no movement. When we have individual forces that are in the exact opposite direction and with equal magnitudes. So here I have 12 newtons to the left and 12 newtons to the right, right? When I add those two together, 12 minus 12 is 0. So I have a net force of 0. If there's no force acting on an object, then that means that the object is not moving. I can't, if an object doesn't have a force acting upon it, it doesn't move. Same thing with this. So I was pulling, the forces were pulling here. Now they're pushing on the object in this one. I have two 10 Newton forces pushing on this object in opposite directions. 10 minus 10 gives us a net force of 0 newtons. Okay? All right. So that is how we figure out how we draw and discuss our two different types of net force. Our third rule, remember, for drawing forces, our first rule is that we can add them when they're in the same direction, like this one over here. We just add them together. In the second one, when they're in opposite directions, we subtract them. These are all in opposite directions. All the rest of these are in opposites. We subtract. But when they are in different directions, totally different, not just left or right or up or down, when it's down and to the right, we can't add or subtract these, so you're not going to get any examples like this on your quiz, or the exam, so don't worry about that. Okay, we talked about drawing forces. What are the rules for drawing forces? Know how to draw individual force diagrams and net force diagrams. We showed you both of those. Our individual force diagrams would be like this. Our net force diagrams would be like this. And if you're still confused by these, there are all of the keys for there's like 5 homework assignments that we did, and I've uploaded all of the keys. So you can go back and look at the friction or the force homework that I gave you that goes over all of these, because I've given you all the answers on there. So if you're still confused, go look at those. All right. We talked about there are 2 main types of forces. We talked about friction and gravity. Friction is where we're going to start. So what is it? It's a force that opposes the sliding motion between 2 surfaces. Okay? They obviously have to be touching one another. So why does friction happen? You need to know why it happens. And the reason that it happens is because these surfaces that are pushing on each other, even if they look super duper smooth, and even if they look like there's no way there could be a bump or a ridge on there, like glass or a mirror or ice, those look so smooth and perfect. But really, at the microscopic level, we have bumps. So if we have, remember this example I gave you was of ice and glass rubbing against each other. Even though they look super smooth, they actually have little tiny bumps on them. And what happens is when these two slide across one another, these bumps actually push on one another. And remember that push or pull is a force. So we have little tiny forces between these two surfaces. And these little tiny forces are called microwelds. So you need to be able to explain, just as I've explained, just right now, why friction happens. So it happens because of these microwelds. The microwelds happen because every surface, no matter how smooth or perfect it looks, actually has microscopic little tiny bumps and ridges that when they slide against another surface that also has microscopic bumps and ridges, we create a force called friction. Okay, then we discussed our 3 types of friction that you need to know about. We have static friction. Static friction is the strongest of the friction forces, and static friction is the force that prevents movement. So it causes a net force of 0, and when we have a net force of 0, we know that we have a balanced force. So an example of this was like if you're pushing a box of books, or you're trying to push a box of books, you're pushing super, super, super hard. You're pushing super hard, but the static friction of the ground, of these micro welds actually, is pushing just as hard and creating a net force equal to 0. So let's draw a little picture. Let's say I have this box of super heavy books, and I'm pushing really super hard on this box. I'm pushing this box, let's say, with 90 newtons of force. The static friction this is on the ground. Obviously, I'm standing on the ground, right? The static friction force is the ground, are the bumps. If we zoomed way in right here, it would be those bumps between the surface of the box and the surface of the ground pushing on each other, right? That static friction is pushing back on me, right? It's pushing back. It's resisting the motion of the box. And in this situation, it would be 90 newtons because we have to have a net force equal to 0 newtons, right? So the static friction in this example is equal to the amount of force that I'm exerting on the box. It causes there to be no motion on the box, or of the box. The box has no motion. Okay, then we have our sliding friction, and this is the middle strength friction. Remember, it's the force that opposes the motion of two surfaces sliding past one another, and it's caused by these microwelds constantly forming and then breaking and changing basically as they slide past one another. So, gonna keep sticking with the same example. Let's say now though, I'm pushing with, let's say I push with 95 newtons of force. I push the box a little bit harder. Well, now the box is no longer going to have, we still have our force of friction here. Let's say that it remains at 90. I'm not going to have a net force equal to 0 anymore. Now if I add these together, the net force on the box is actually going to be 5 newtons to the right? Because 95 minus 90 would be 5. So now there's a net force. If there's a net force, that means that we have an unbalanced force, right? So this causes motion. This is an example of sliding friction. This is sliding friction that causes the box to slide across the floor. And finally, we have rolling friction. Rolling friction is the weakest friction force, and it occurs when an object rolls on a surface. Like if I put this box on wheels, then I would be rolling it. And this actually would decrease. It would be rolling friction now, which would be less than the static or the sliding friction. So the friction here would be at the wheels, and maybe it would only be 10 newtons. So I would push the box with an overall net force of 85 newtons to the right. Okay? And here is a quick, remember this nice, these nice diagrams that I gave you. This is, if you want to pause and take a look at these, that would be great, but this is already just stuff that I have just already shown you. Or explained to you, not shown you, but okay. So that's really all you need to know. That's it. That's what you need to know about friction. The other main type of force that we discussed is gravity. Right? So we have gravity. Gravity is an attractive force between any two objects. And remember we said that it depends on the mass of the two objects and the distance that between the two objects. It acts on all objects with mass, so meaning that gravity acts on all matter in all objects. And we had this law, Newton's law of universal gravitation. Remember, he came up with this he came up with this and calculus and Newton's laws of motion during the bubonic plague. So remember that the universal law of gravitation, or the law of universal gravitation, is that it's this formula, but we don't need to know this formula. We don't need to be able to mathematically manipulate this formula. We just need to understand what each component of this means, and then we need to be able to explain it and use it when discussing gravity between two objects. So remember, Remember, Isaac Newton was studying motion between planets, and he was doing this to determine the relationship. Oof, Ailey's not happy. The relationship of gravitational forces between the two objects. So he did this by looking at motion between planets. And let's break down again his universal law of gravitation. He says that gravitational force between two objects, big F, is equal to this gravitational constant, which we don't need to know the number value of. We don't need to know that. We just need to know that it is a gravitational constant that is constant throughout the universe. And we multiply that gravitational constant by m1, m2. This is the mass of object 1. m1 is the mass of object 1. And m2 is the mass of object 2. And we divide that by the distance squared between these two objects. All right, so remember, that's the equation. That's what the equation tells us. Remember that we looked at two relationships. We looked at the relationship between the mass and the distance, okay? So we said that if we increase the mass of object 1 or object 2 or both objects, we would increase the gravitational force between them. This was a direct relationship. Another way you might see me writing this is a directly proportional relationship. All right, so this is a directly proportional relationship. As mass increases, force increases. Remember, and then we looked at distance. If we decrease the distance between the two objects, if we move the two objects closer together, right? So if we move them closer together, we increase the force. We increase the force between the two objects. So this is an inverse relationship, or you may have heard me also say an inversely proportional relationship. All right? Okay, so you need to understand that if I increase the mass of object 1, I will increase the force between the two objects. If I increase the mass of object 2, but keep the distance the same still, I will increase the force. If I increase both masses, I'll obviously increase the force even more. If I decrease the distance, if I put them closer together, I will increase the gravitational force between them. But if I pull them farther apart, if I separate them further, I will decrease the force between them. All right? Okay. That is all you need to know about yes, we did all of these examples. You can go back and watch this video again not this one that I'm doing, but the video where I talked about the law of universal gravitation. You can go back and watch that if you'd like some specific examples, right? So why do we feel gravitational force between me and the earth, but not between me and the sun? That kind of stuff. You can go back and rewatch that video if you would like. Okay. Then we also talked about gravitational fields. And remember that because contact between two objects is not required, we discuss gravity as a gravitational field. And a field is a region of space that has a physical quantity. In this case, it's a force at every point. And here is a nice diagram of what a gravitational field looks like. The gravitational field of Earth weakens as we get further away from the surface of the Earth, right? So if I'm standing right on the surface of the Earth, we are at 9.8 newtons per kilogram. Remember, this is the strength of gravity that we use in all of our calculations. But as I go higher into the atmosphere, see I'm at this first ring here, I decrease gravitational strength. And even higher, I decrease it, and now I'm out of the atmosphere. And this would be like what the moon feels, for example. So the moon feels Earth's gravity, but it's very small compared to what we feel here on the surface of the Earth. All right. Remember that gravity can be different. Gravity is different on different planets. So the reason that the moon, we've talked about this several times, the moon has less gravitational strength. Remember, it's I think I've told you, it's 1/6 the strength of, so gravity on the moon is 1/6 the strength of gravity on Earth, right? So that means that it's gravity on the moon, G on the moon. G on the Earth, remember, is 9.8 at the surface of the Earth. But 1/6 of 9.8 is 1.6 newtons per kilogram. So on the moon, the strength of gravity on the surface of the moon is much less than the surface of, or the strength of gravity on the surface of the Earth. And the reason for that is because the moon has much less mass than the Earth, right? The moon is a lot smaller. It's like, I'm drawing, this is supposed to be the moon. I don't know. That's not a great diagram, but you get the point. Anyway, so when it says on the study guide, gravity on different planets, I just want you to know that we can have different gravitational strengths. We do have different gravitational strengths on different planets. Then we talked about weight. So what is weight? Weight is the gravitational force exerted on an object. It is the object's weight. The formula is Fg, or force of gravity, or weight, times mass, times gravitational strength. And this value, remember, this is little g, it's 9.8 newtons per kilogram. This is g on Earth's surface, but g on the moon's surface would be 1.6 newtons per kilogram. So it depends on the type, or on the planet, or where we are looking. Remember that weight is not the same thing as mass. Weight is a force, and I think I rewrote this up here. Yes, weight is a force. Mass is the measurement of the amount of matter inside an object, right? So mass is the amount of stuff inside of an object, and weight is the force of gravity acting on that stuff, okay? So they're related. There's a directly proportional relationship between mass and weight. So as mass increases, so does weight. But we have to be very careful not to confuse the two. And I will ask you some questions on the quiz to make sure that you understand this. So it's really important that you know the difference between the two. So if you want some examples of me going through the problems, you can go back to this day in the lectures when I talked about weight, and you can rewatch that lecture video if you need some further, or going through the problems, because you are going to need to be able to use this equation here to solve for whatever I ask you to solve for on the quiz. All right, so you need to know how weight changes on other planets with gravity that's different from Earth's, like I was telling you. So here I gave you, again, I thought that said mom. The gravity of mom. Oh, that's like a bad your mama joke. Okay. Anyway, so gravitational strength on other planets and moons varies. So I already kind of discussed this. I will give you a problem, excuse me, sorry, like with the moon or Jupiter, and say, okay, so the gravitational strength of the moon is 1/6 that of the Earth. So what is the gravitational strength of the moon? Well, that's really simple. You just 1/6 times 9.8 and you get 1.6, right? But obviously I'm not going to give you the same one that I keep giving you over and over again. So I'll probably give you a different one. I'll say that Mars's or Saturn's gravitational strength is 3 times as strong as that of Earth. So if something is 3 times as strong as G Earth, and we know that G Earth is 9.8 newtons per kilogram, then we know this is about 30. I'm not going to calculate it. It's 20. Ugh. All right, so it would be 29.4 newtons per kilogram. I solved. Okay, so you're going to need to understand how to do that. And then the problem will say something like, calculate the weight of the boy on this planet, or whatever I said. I think I said Saturn, right? So calculate the weight. So you need to understand how you can solve for different gravitational strengths based on a word problem, like I've said. So here I say, on the moon, gravitational strength is about 1/6 that of gravitational strength on Earth. So you need to understand how you can calculate the gravitational strength on the moon based on this word problem, and then you'll be able to use this new G of the moon or G of Saturn, like I did over here, to solve for whatever you're looking for in the problem. All right, so that's everything. That is a complete review of 3.1. I will post a complete review of 3.2 tomorrow, and 3.2 and 3.3 tomorrow. So that is all for today. Please let me know if you have any questions, and I really strongly recommend going back and looking at those keys that I've uploaded. Those are going to be helpful for you to understand the problems that you'll see on the quiz. Let me know if you have any questions. Thank you.